In this chapter, we're going to examine acids and bases. This is a topic that you have covered to some level in Gen Chem, so hopefully a lot of this stuff will seem pretty familiar. We'll definitely take an organic chemistry spin on this. You'll kind of, in addition to seeing the sort of quantitative approach you've seen in Gen Chem, we're also going to have a bit of a qualitative approach when examining how a lot of organic compounds can exhibit acidic and basic behavior. So you'll kind of get a way to sort of qualitatively look at organic compounds and at least comparatively tell which ones are going to act acidic or basic in particular scenarios. Okay, and of course we're still going to use the quantitative approach as well. So you're going to deal a lot with pKa's and things like that. So hopefully all that stuff should ring a bell from Gen Chem. But if not, don't panic. We're going to cover it all again. So here we go. So to go back to Gen Chem, you might recall that there are different ways to define what is an acid and what's a base. There are three main ways, actually. You probably are most familiar with the Arrhenius definition, where an acid is something that gives off H plus, and a base is something that gives off OH minus, right? Well, the Bronsted-Lowry definition is probably the most common definition that you've seen, and I think especially in Gen Chem, this was probably a definition that you really covered in a little bit more detail. So just to jog your memories, the Bronsted-Lowry definition of an acid and a base looks at where a proton is going. Now, a proton is the same thing as an H plus ion, because remember, the most common isotope of hydrogen is hydrogen 1, which is just a proton and an electron with no neutrons. So if you remove that one electron, all you have left is a proton. Okay, so that's why a hydrogen ion, an H plus ion, is often called a proton. Okay, now that being said, protons themselves aren't particularly stable. So in aqueous solution, they tend to clip onto water molecules to form a hydronium ion, as you can see over here. But the key thing, though, is in this Bronsted-Lowry definition, we're going to pay attention to where that H plus is going. All right, so while the Arrhenius definition uses H plus to describe acids as well, it focuses on OH minus or hydroxide for bases. Here in the Bronsted-Lowry definition, we're going to watch where the H plus is going and what is accepting it. The acid is the thing that gives off an H plus. It donates a proton. A base accepts that proton. Okay, and that's where it's a little bit different from the Arrhenius definition. So let's look at the example here. Over here we have HCl, okay, hydrogen chloride, and we have water. Okay, now if we look on the product side, we see that the HCl lost its H plus to form a chloride ion. Okay, and likewise the water accepted that proton to become hydronium. So in this example, your hydrogen chloride is acting as an acid. It's giving its H plus, it's donating its H plus to your water molecule. The water molecule in this scenario is acting as a base. It's accepting that proton in order to form hydronium. Okay? Now, again, if you're kind of fixated on the Arrhenius definition, you're probably thinking, wait a minute, isn't water neutral? Water is actually what we call amphoteric. It can act as an acid or a base depending on the situation. And in this situation, where it's paired up with a strong acid, it will act as a base. All right. This sort of this kind of dynamic where things paired up with a stronger acid or stronger base, forcing them to act one way versus another, is a kind of a common theme you're going to notice in a lot of organic chemistry acid-base equilibria. We're usually dealing with weak acids and weak bases, and these are going to exist as equilibria. And so we'll often try to compare relative acidity and basicity to decide which way this equilibrium will shift. Anyway, more on that in a little bit. You'll see some examples, and you'll see what I mean. Okay, so basically, like I said, you want to keep an eye on where your H plus is going. What's giving off an H plus and what's gaining an H plus. Now, in the previous example, HCl, we identified our HCl as an acid and the water as a base. Now, notice that this is represented as an equilibrium. Okay, now normally hydrochloric acid is a strong acid, so this would be just a regular arrow. But for the sake of argument, let's assume that this is an equilibrium, which means that this is a reversible reaction. Okay, now what does that tell us about the products of this reaction if we looked at the reverse reaction, where they are now the reactants in that reverse reaction? So in the reverse reaction, chloride would gain an H plus from hydronium to go back to being HCl. Okay, so in this scenario, chloride would act as a base in that reverse reaction. Likewise, our hydronium would give off that H plus. It would donate that H plus to the chloride when it goes back to being water. So in the reverse reaction, hydronium would act as an acid. So we call these products conjugates. So chloride is the conjugate base, hydronium is the conjugate acid, because they act as bases and acids respectively in that reverse reaction. Okay, so why don't we take a second and practice this? So feel free to pause this video and try and determine which of these are acids, bases, conjugate acids, and conjugate bases. Remember, your acid and base are on the left-hand side of your equation. Your conjugates are always on the right-hand side. Okay, based on the way your equilibrium is defined, conjugates are always on the product side. Okay, so feel free to pause this and take a stab at it. Okay, so if you've hopefully already guessed, your answers, you basically have to see that our water molecule here is donating this H plus to this tert butoxide ion over here. So water here is acting as an acid. The tert butoxide, because it's picking up that H plus, is acting as a base. And of course, in the reverse reaction, their roles are kind of flipped, right? What used to be the base is now the conjugate acid. The resulting hydronium that forms, hydroxide that forms, is the conjugate base of your water. This OH ion would pick up this H plus to go back to being water. So since it's going to accept an H plus in that reverse reaction, it's a conjugate base. Okay, so you can kind of figure out what's going to happen if you are told which is your acid and which is your base. By definition, that tells you that that material is going to lose an H plus or gain an H plus respectively. Okay, so you want to keep an eye on, you can kind of figure out your conjugates accordingly by being told how these things are going to behave. All right, so here are two potentially amphoteric species. We're going to see what would happen if, in this scenario, water acts as an acid to our amine over here, and in this scenario where water acts as a base to our amine. Okay, so basically, here I should probably avoid saying using that expression basically, because we're talking about bases obviously, so not to be confusing, but essentially what's happening here is if water's acting as an acid, it's going to lose an H plus. So that H plus is going to be plucked off here, which means that what's left behind, instead of being neutral as it is here, will have a negative charge. Okay, so we remove a H plus ion. If you want to see this with an arrow pushing diagram, we can let me draw that in here so you can see what's going on. Basically, or essentially, the electrons from this oxygen-hydrogen bond are going to go to your oxygen. Okay, so they're going to wind up as an extra lone pair, right? Likewise, that hydrogen ion will wind up going to this nitrogen. Now, how does that nitrogen pick up that hydrogen? Well, it forms that bond because a lone pair on the nitrogen will donate to that. Okay, and so that's where that nitrogen-hydrogen bond forms. And notice that that lone pair is missing because that lone pair went into forming that bond. Okay, now of course in this process that nitrogen then picks up a formal positive charge. Okay, and you can tell that this is a well-balanced equation because notice our charges are conserved, right? We started off with two neutral molecules and we wound up with a positive ion and a negative ion. Okay, now let's have a look at that as a in reverse, where our amine is going to act as an acid. So remember, in this scenario now, this amine is going to lose that H plus. So we're going to break this bond here. Okay, and that's going to donate as a lone pair to that nitrogen, as you can see here, giving it that negative formal charge. And here it's the water that donates its lone pair on the oxygen to that hydrogen to form a bond. Okay, so there we have the resulting hydronium ion that's formed. Okay, and again, you can see that that oxygen has that positive formal charge, and you can tell this is a good equation because it's still balanced. We started off with two neutral species, and the overall charge on the right is still neutral, the negative and the positive canceling each other out. Okay, so that's essentially what's going on here. In all of these acid-base reactions where an H plus is being transferred, there's a transfer of electrons going on here. You're breaking a bond between the hydrogen and what's going to become the conjugate base, and you're forming a bond between the lone pair on your base and your hydrogen ion. Okay, and that forms the resulting conjugate acid. So that's something to keep in mind with these curved arrows. When you're drawing these curly arrows, that's where the electrons are going. You can say that a base is attacking the acid. It's sort of plucking off that proton. It's ripping away the proton from your acid. Okay, so that's one way to sort of think of it. Again, it's easier to say that when you see those curly arrows and you see like the base is kind of attacking that proton with its lone pair. Okay, so let's practice this. I guess I've kind of already shown how this happened, but if you want to practice drawing this out yourself, again, remember that your electrons, if you want to draw this in one concerted process, make sure you draw your arrows originating from your acid, or from the lone pair in your base, sorry, towards the bond that your proton is about to break with its acid. Okay, so if you want, please feel free to pause this while you try drawing this out yourself. This is again very similar to one of the examples we did earlier, but yeah, feel free to pause here. Okay, and if you've come back and you want to see this drawn out, again, remember you want to have that arrow originating from your lone pair on your base going towards the proton, right? Because that's the bond you're going to form between your, that atom and the hydrogen in your resulting conjugate acid. And of course, you want to draw another arrow from that bond that you're about to break with that hydrogen going to the atom it's bonded to, and it'll wind up being an extra lone pair on that conjugate base. All right. So if you want to see that drawn on the original molecule, just so you can compare what it would have looked like if you were drawing on this slide, it looks something like this. Okay, so remember, this is your base. That lone pair is going to go towards this proton that is going to pick up, and this bond with the oxygen is going to go to that oxygen. All right, so that's how you would draw that resulting, those arrows. Okay, and so from there you realize, all right, this is going to have an extra hydrogen here. So if I start off with that molecule, there's an extra hydrogen attached to that nitrogen, and I don't need another lone pair because that lone pair went into forming this nitrogen-hydrogen bond. Okay, so this is my conjugate acid, right? Because in the reverse reaction, it would lose that H plus again. And of course, water, now it's lost that H plus, and this is going to wind up being an extra lone pair in that oxygen. So if I draw the rest of that water molecule, okay, we're breaking that oxygen-hydrogen bond, and there's going to be an extra lone pair here. Okay, now of course don't forget formal charges. This nitrogen has 4 bonds and no lone pairs. That's why it has a positive formal charge. This oxygen has 7 electrons around it if you break that bond in half, so it has a negative formal charge. Okay, and of course that's your conjugate base. Okay, so I can have that in the next slide, obviously, but that's what it would look like if you're drawing it manually. Okay, in a similar step, let's see if you can figure out which of these. So here we have like a full mechanism for a reaction. Only some of these steps might be acid-based steps. So remember, in a Bronsted-Lowry definition of an acid, there is a proton transfer going on, right? And H plus is being moved from one atom to another, identify those acid-base steps here. Okay, so have a look at each of these and see if you can figure out which ones involve a proton transfer. Okay, so if you pause the video and come back now, hopefully you'll have seen that basically we have a this oxygen here is picking up this hydrogen, right? Notice that we're breaking this bond. Okay, so this here is a proton transfer step. All right, you can see those that conservative set of two arrows where that lone pair is forming this bond with the hydrogen, and this bond with the hydrogen's breaking, going and forming a lone pair on that oxygen. Okay, and getting this to leave as water. This step over here is not an acid-base step. We're breaking this carbon-oxygen bond. There's no transfer of H plus in that step, so therefore this is not, the second step is not an acid-base step. If you're curious, this is the loss of a leaving group. That's what we would call this step. In a later chapter, we'll go through all of the steps that the types of steps you'll see in mechanisms like this, and learning to identify them will get a lot quicker and easier. Okay, so don't stress that this is called the loss of the leaving group. We'll learn about that later. Okay, what about this third step here? So here we have this carbon-hydrogen bond breaking, and you can see here that this oxygen is picking up that hydrogen. Okay, so again, notice we have that concerted set of two arrows, right? The two arrows acting in the same step, where we were forming a bond between, the lone pair on an atom going to a hydrogen, and then that bond breaking, of that hydrogen with something else, and it's dropping off those electrons somewhere else. So this second step is also an acid-base step. This third step is an acid-base step. All right, so to answer this question, which of these three steps are acid-base steps? The first one and the third one, okay, not the second one. Okay, so let's try and quantify acidity. Let's see if we can, eventually we're going to try and compare things as acids or bases, which things are stronger acids, which ones are weaker acids. One way to do this is we can do it quantitatively, right? We can use Ka values, or more commonly we'll use pKa values, and those numbers give us a direct means of comparison. Okay, generally the lower a pKa, the stronger an acid. Okay, we're also going to look at qualitative tests for doing this. I'll teach you a method of analyzing a molecule to kind of gauge how strong of an acid it is compared to another similar molecule. Okay, but first things first, let's go over the quantitative stuff. Again, hopefully this should ring a bell from Gen Chem, but again, if not, let's talk about it. So when we have a weak acid reacting as an acid, we can write out that equilibrium, and as such we can take that equilibrium and write out an equilibrium expression for it. So just to jog your memories from Gen Chem, whenever you have an equilibrium, the equilibrium expression involves some constant K, and it's your concentration of your products raised to whatever coefficient they have, divided by the concentration of your reactants, again raised to whatever coefficients they have. Here the coefficient of everything is 1, and that's why the superscripts are all ones, so to say that they're not squared or cubed or anything like that. Okay, so we have our products here. We have our conjugate base and we have hydronium, so both of those go on the numerator. And on our reactant side, we have our acid and water acting as a base. Notice that we only write our acid on the denominator. Okay, why is that? Remember, these square brackets stand for concentration or molarity, right? And water, being a liquid, doesn't have a concentration, right? So it's only aqueous solutions that you can put into these square brackets here. Technically, you can put gases as well, but for the most part, you're going to see aqueous things. Okay, so since this denotes an acid-base reaction, or rather an acid acting as an acid, we put a subscript A here instead of just writing the general K for our equilibrium constant. So we call that a Ka, or an acid dissociation constant, as it's sometimes called. Okay, and so this kind of gives you a numerical idea of how strong an acid you're dealing with. Because remember, an acid is something that gives off hydronium, and a strong acid gives off lots of hydronium. Okay, so if you have a really strong acid, you're going to have a lot of these products, right? This reaction is going to go closer to completion. Instead of having an equilibrium arrow, for a strong acid, you typically write it as just a regular reaction arrow. So with that in mind, what happens to your concentrations? Well, your hydronium and conjugate base are going to have large concentrations. So if these numbers on your numerator are very large, what's going to happen to the value of Ka? Well, it will also be a large number, right? So that's something to keep in mind. Right? Now, because we're dealing with a very large range of Ka values typically, and we're dealing with some really ridiculous numbers, either very, very small or very, very large, it sometimes helps to work on a logarithmic scale. Now, to do this, we take the negative log of our Ka. This gives us what's called the pKa. All right, the P in pKa stands for potens, or power in German. So P of anything is just negative log of that thing. So if you recall, pH is just a negative log of H plus ions. Okay, the concentration of H plus ions. So a quick note here, when I say negative log, that's log base 10. Okay. All right, so you just take the negative log base 10 of your Ka value, and that'll give you a pKa. All right. Now, please note that negative sign there. This kind of flips the pattern that we see. Remember, a large Ka value indicates a strong acid. Because of that negative sign, a strong acid with its large Ka value would give a very low value for pKa. All right. So, for example, hydrochloric acid, which is a strong acid, has a pKa value of -7. Okay. Sulfuric acid, which is an even stronger acid, has a pKa of -9. Right? So we're dealing with very low pKa values. Right? So here are some examples of pKa's if you want to compare them. Normally, it helps to kind of memorize a few of these, at least just for comparison's sake. Just like, for example, knowing that sulfuric acid and hydrochloric acid as inorganic acids, it's kind of good to know, what these strong acids kind of are comparatively. But generally speaking, as long as you know that they're very negative, that usually tells you all you need to know, because they're strong acids. I recommend knowing the pKa of hydronium. I recommend also knowing the pKa of water at 15.7. Okay, you can kind of figure out that most alcohols are going to be somewhere in that ballpark. So if you remember water is 15.7, you can kind of figure out what the others are. Likewise for alkynes, alkenes, and alkanes, knowing that they're in the 25, 45, and 50 ballpark usually helps. Okay. Again, I think carboxylic acids are another one that's probably a good one to know, knowing that somewhere in that 5 ballpark for a carboxylic acid functional group. Again, we'll look at some of these functional groups in more detail. I think especially in this case, with some of these, we'll only get into them in the next semester in Chem 204. So don't panic too much about them. And like I said, I will give you a qualitative way to do this. But like I said, memorizing some of these pKa values kind of helps with that comparison. Okay. Oh, a quick note here about comparative numbers. Remember, this is a logarithmic scale. Okay, so in the case of sulfuric acid and hydrochloric acid here, even though it's a difference of 2 pKa numbers, remember that's 10 to the power of 2. So sulfuric acid is actually 100 times a stronger acid than hydrochloric acid. Okay, so something to keep in mind, even though the logarithmic scale shrinks the numbers you're dealing with, you have to realize that in real life then that the difference is exponential. Okay. uh, if you look at an acid and you want to figure out how basic is its conjugate base, typically speaking, a strong acid wants to really go towards its conjugate base. So the reverse reaction is not going to be very strong. So typically the conjugate base of a strong acid is pretty weak as a base itself. Okay, so conjugate acids, strong acids give weak conjugate bases. Likewise, weak acids give pretty strong conjugate bases. All right, they really want to do that reverse reaction to go back to forming the original acid. Okay, so for example, we pointed out that alkanes like this one have very high pKa values. The resulting carbanions are really strong bases as a result. Okay, now I mentioned that a lot of what we're going to do here in organic chemistry is to compare different acids that are in equilibrium with each other in order to figure out which way an equilibrium will shift, which of these molecules is going to act as an acid and which one's going to act as a base, right? So let's have a look at the acid and the conjugate acid in this reaction. So on the left, we have water acting as an acid as it forms hydroxide, its conjugate base. And remember, water has a pKa of 15.7. Now, on the right-hand side, we have tert-butanol. Tert-butanol, as an acid, has a pKa of 18. Okay, so even though we're starting off with tert-butoxide as a base here, and by the way, don't panic if you don't have these names down yet. We'll learn about that when we get to the chapter on alcohols and stuff. But for now, just realize just realize that in this forward reaction, we have this molecule here acting as a base, but we want to see how is this going to act as an acid in that reverse reaction. Well, tert-butanol here has a pKa of 18. So, which of these two is the stronger acid? Is water or tert-butanol a stronger acid? Well, remember, a lower pKa tells you you've got a stronger acid. So water really wants to give off its H+, at least compared to the alcohol over here. So this equilibrium is not even, right? This equilibrium is actually kind of shifted to the right, shown by this bigger forward reaction arrow compared to the smaller reverse reaction arrow. Okay? So in this scenario, you're going to have more of your products than you are of these reactants. Okay. Now, how much more? Again, we can compare these pKa values and say it's going to be, since we have a difference here of 2.3, it would be 10 to the power of 2.3. So somewhere in between, 100 and 1,000 times. So here's another example of an acid-base reaction. Though here you can see, where that difference in pKa really changes our equilibrium arrow. So for example, here we're dealing with water as an acid again, and notice it's got a much lower pKa compared to our conjugate acid here, this alkane with a pKa of around 50. So there's a huge difference here in pKa values, right? About a 34-point difference. So 10 to the power of 34 is a huge number. So it doesn't make as much sense to write this as an equilibrium arrow. It makes a lot more sense to just put this as a one-way reaction, because this reverse reaction is pretty much not happening. Okay, but again, the point here is that you can use these comparative pKa values and their difference to kind of figure out which way this equilibrium, or in this case reaction, is going to go. All right, now sometimes you don't have pKa values in front of you. You might not be able to look them up, or you just, it might be something that doesn't have a known or easy to look up, pKa value. Can you figure out how things are going to behave from an acid and base standpoint just by looking at them? Well, it turns out that there are certain patterns that we notice when comparing molecules and seeing which one's a better acid or which one's a better base. Okay, and there's also kind of a checklist or kind of a hierarchy or flowchart to figuring this out. A way to sort of troubleshoot what at what point do I see a difference between these two molecules, and how does this difference mean that this molecule is a better acid or this one's a better base? Okay, so let's have a look at each of those. So if we, there are kind of two ways to look at this. It depends on whether your molecule has a formal charge or not, but typically either your starting acid has a formal charge, and when it loses a proton, it goes from being positive to, let's say, being neutral, or it might be a neutral molecule, and when it loses a proton, it forms a negatively charged conjugate base. So the approach we're going to take here is asking ourselves, how good is this molecule at supporting that formal charge? Okay, how good is it at stabilizing that formal charge? So let's look at an example here. Here we have hydrochloric acid, and here we have an alkane. Okay, basically, if we lose an H plus from each of these, okay, what is your resulting conjugate base going to look like? All right, so hydrochloric acid, when it loses H plus, will form Cl minus. Our alkane over here, when it breaks this carbon-hydrogen bond, right, the carbon over there is going to turn into a carbanion. Now, which of those is going to be better at stabilizing the negative charge? Well, you know that chloride is probably a pretty stable anion, but a carbide anion is not very stable. Okay, so just from that alone, you know that HCl is going to be a better acid because the resulting conjugate base is more stable. Whereas here, since this conjugate base is so unstable, it really wants to go back to reforming the protonated version of this molecule, and therefore the protonated version is not a good acid. Okay, so when it comes to doing this, we have this sort of checklist of things that we examine to see what is good at supporting this negative formal charge on our conjugate base. The checklist is summarized in an acronym called ARIO, okay, where we look at the atom involved, that's the A in ARIO, if there's any resonance, then we look at induction effects, and finally the type of orbital that is housing the charge that we're looking at. Okay, so typically we kind of go down this checklist. So we first look for different atoms. If the atoms are identical, we then look for resonance differences between the two molecules. And if that's the same for both molecules, then we look at induction. And if that's the same, then finally orbital is the last tiebreaker that we use for figuring out which one's a better acid. All right, so let's look at each of these examples in turn. So the A in ARIO comes from the type of atom that's carrying the charge you're looking at. So let's compare these two molecules. Here we have butane, which is an alkane. So notice that the hydrogen we're going to break off here is attached to a carbon. Here we have propanol, which is an alcohol, and here the hydrogen is connected to an oxygen. So when we break these respective bonds with hydrogen, the resulting conjugate base will have a negative formal charge on the other atom. So, is a carbon better at stabilizing a negative charge, or is the oxygen better? Well, when you compare two atoms, you want to compare them based on their electronegativity if they're in the same row, or if they are in different rows, you kind of want to go off of which one has more electron density to push around, which one is squishier, if you will. Okay, so if it has more shells of electrons, typically it is better at diffusing that negative charge. All right, so in this example, we're looking at carbon and oxygen, which are both in the same period. So here we're going to compare them on electronegativity. Now remember, atoms generally increase in electronegativity as you go to the right in the periodic table. Okay, that's why fluorine is the most electronegative of all the elements. Okay, so oxygen, being to the right of carbon, is going to be more electronegative, and therefore your propanol is going to be a better acid than your butane. Okay, and if you want to confirm this, you can look up their pKa values. You'll see butane's got a pKa somewhere around 50, Propanol has got a significantly lower pKa, somewhere in the ballpark of 16. Okay, now let's say the proton you're plucking off is on the same type of atom for both molecules you're comparing. So here we have ethanol and acetic acid. In both cases, our acidic proton is attached to an oxygen. So the A in REO doesn't really help us. Okay, so the next thing we look at is resonance. Is that negative charge going to be resonance stabilized? In the case of ethanol, it is not. There's no place for that negative charge to be shifted through resonance. However, look at your acetic acid, or if you're having trouble seeing it, look at the resulting acetate ion that you would get if you lost this H plus ion. So if we get something to pluck off this proton, oops, sorry, I did that the wrong way. So if we get something to pluck off this proton, so these electrons go to that oxygen, okay, your resulting anion is going to look like this. Okay, with a negative formal charge to that oxygen. Well, we can now shift that negative charge through resonance. This lone pair can form a double bond here, and this double bond's electrons can shift to this oxygen here, and so we get a resulting resonance structure that looks like this. Okay, so notice that here that negative charge is sort of split between both oxygens due to resonance. So this delocalization of those electrons, spreading out that electron density, spreading out that formal charge, helps stabilize the formal charge. Even though oxygen is electronegative, even for the ethanol, in the case of acetic acid, that spreading out of that negative charge makes this acetate a much more stable conjugate base. Okay, and that's why acetic acid is a much more acidic acid. I think if you can compare pKa values, acetic acid is probably somewhere in that ballpark of about a 5 pKa compared to ethanol, which is somewhere in that 16 ballpark. Okay. Let's say now you have two molecules that have, that are tied with the A and the R of REO. So for example, here we have two types of carboxylic acids. We have acetic acid, where again our hydrogen, our acidic proton is attached to an oxygen. Okay, and again for trichloroacetic acid, once again our acidic proton is attached to an oxygen. All right, so the A is tied. Okay, if we look at resonance, both of these have that sort of, they are one bond away. They're in that not very like the allelic position compared to this double bond with oxygen. Okay, so you know that they're going to have resonance with this other oxygen, and both of them have that scenario. So that's also tied, right? We can't use resonance as a tiebreaker here. So the next thing to look at is inductive effects. Do we have any electronegative elements that are within a couple of bonds of our negative formal charge? Okay, and in this case, with trichloroacetic acid, we have three very electronegative chlorines that are one carbon away from that resonance system. Okay, so if we look at that oxygen is going to have a negative formal charge, or 1, 2, 3 bonds away from these electronegative chlorines. These chlorine atoms, being very electronegative, are going to sort of pull electron density towards them, and that in effect helps delocalize that negative charge. Okay, not to the same extent that resonance does, and this is why resonance is a higher priority in our acronym, but induction does kind of carry out a similar function. It helps spread out that negative formal charge. Okay. Regarding induction effects, for acetic acid, we kind of use the R in REO. We use resonant to explain why acetic acid is a better acid. There's also a little bit of induction here from that electronegative oxygen. So that probably also plays a little bit of a role. But again, the resonance is a much bigger deal, so it kind of overshadows that. Okay, so you can see this when you change the numbers and locations of electronegative elements. So in this case, we keep on adding more and more chlorines to this same position. And you can see that as we add chlorines, our pKa keeps on dropping. Okay? So we get lower and lower, and therefore our, you know, we're getting into a stronger and stronger acid because of that greater inductive effect. Okay. We also notice this if we use more electronegative elements. Okay. So notice that we have, if you took fluoroacetic, so here we have chloroacetic acid with its pK of 2.87. If we swapped out that chlorine for a fluorine, that pKa drops to 2.6. Okay. However, if we use bromine, which is less electronegative than chlorine, notice that the pKa only the pKa is actually 2.89 compared to 2.87. Okay, so accordingly, you want to keep that in mind, that electronegativity affects this induction effect. Now, I think what gets a lot of students is that the A in REO doesn't look just at electronegativity, but it also looks at atomic radius, right? So for example, if I were comparing hydrochloric acid with hydrobromic acid is a stronger acid than hydrochloric. It's got a lower pKa because bromine is a larger atom, okay, and it's able to house that negative charge better. Here, bromoacetic acid is a weaker acid than our chloroacetic acid, okay, because in the case of induction, since the bromine's not housing that negative charge, it's just having an inductive effect, electronegativity is what matters here, not the size of the atom. Okay, the size of the atom doesn't help your atom, contribute that inductive effect. So something to keep in mind when you're comparing two acids based on the atom that's housing a negative charge, if you're using the A in REO, or if you're looking at inductive effects, the I in REO. The last thing we look at then, if we're tied with everything else, the last tiebreaker is the orbital that we have. All right, so basically, the more stable, if you have a negative charge closer to an atom's nucleus, that's going to kind of, that those opposite charge. Let's pause here. I need to read up on this a little bit. So the last effect that we look at, the last tiebreaker that we use when qualifying acidity is orbitals, right? So all other things being equal, we can compare the type of orbital that's housing that negative charge. Okay. Typically, the smaller an orbital, the closer it is to the nucleus, the lower it is in energy, and therefore the better it is at housing that negative charge. So if we were comparing an s orbital versus a p orbital at that same level, so let's say comparing a 2s orbital and a 2p orbital, that s orbital is going to be much better at housing that negative charge. Okay, it's good in keeping it close to the nucleus. Likewise, with hybrid orbitals, the more s character that those hybrid orbitals have, the smaller they are and the better they are at housing a negative charge. So you can see here, if we compare an sp orbital, which is kind of half s character, sp2, which is about a third s character, and sp3, which is only a quarter s character, it looks a little bit more like a p orbital. It's like 3/4 of a p orbital. You can kind of see that we get kind of smaller and rounder with that sp orbital. Generally speaking, this is going to be better at housing that negative charge. Okay. If you ever have trouble remembering that, a good way to check is using known pKa values. This accounts for the difference we see in an alkane versus an alkene versus an alkyne. Okay. In each of these cases, we're going to pluck a proton off an sp, sp2, or sp3 hybridized carbon. And you can see that in the case of an sp carbon, our pKa is much lower compared to an sp3 hybridized carbon. Okay? Because otherwise everything else is pretty much equal, right? Your negative charge is going to be a carbon on a carbon, so you can't use the A in REO. There's no resonance for this, even for the alkenes and alkynes, because The negative charge is on your vinylic carbon, not your allylic carbon. Okay, so there's no resonance. There are no electronegative elements attached to this, so there's no induction. So the only tiebreaker here is that O from REO, the orbital that's housing that charge. Okay, so something to keep in mind if all of the tiebreakers fail. Okay, so with that in mind, if you have a molecule that has that has multiple sites, multiple protons that can be plucked away, you want to keep that in mind. Which sites are available? What are the pKa's of the protons on your molecule, and therefore which ones are your base more likely to attack? So if you look at a molecule like this, ask yourself, well, where's the proton that would be most likely to be attacked? So again, notice that we are dealing with a hydrocarbon here. So the A in REO is taken out because you've only got hydrogens on carbons, right? So they're all the same type of atom. Again, you want to be careful of resonance effects because that might take precedence over SP. So for example, you might be tempted to say, well, these SP carbons don't have hydrogen, so that's not an issue. But if I look over here, this sp2 carbon has a hydrogen. Oh, that must be my most acidic proton. What you've got to watch out for is that your hydrogens here would be resonance stabilized with this double bond. Likewise, the hydrogens here would also be resonance stabilized with this double bond, and this one here too. So keep that in mind. If you have a negative charge over here, here, or here, that double bond's going to kind of help, stabilize that negative charge. Okay, so that's something to keep in mind. That being said, I think they basically, when they made this slide, I think they wanted to focus on the orbital aspect. So I think they ignored the resonance effect here. If we were looking just at orbitals, this sp2 hybridized carbon is going to be, that proton is going to be more acidic compared to any of these sp3 hybridized ones. Well, not the resonance stabilized ones, but like let's say this one over here, which is kind of isolated from all that. Anywho, my point here is that this is still, even with this hybridization, even with this sp2 hybridization where that orbital has a pKa that's a little bit lower, that's like, let's say in that ballpark of about 45 instead of 50, 45 is still a pretty high pKa. You're still going to need a very strong base to do this, to deprotonate there. So something to keep in mind. Okay, so again, the key thing I'm trying to get across here is that you want to keep in mind when you have multiple functional groups, when you have multiple sites on your molecule, that there's some competition for different possibilities that we have going on here. So in the case of acids and bases, at least, be aware that you might have more than one site that can act as an acid or can act acidic. Okay. Likewise, there are parts of the molecule that can act basic. So, for example, your pi electrons could be opened up to form sigma bonds, and therefore can pick up protons that way. All right. All right. We will probably talk more about that in later chapters too, though, and we'll see examples of mechanisms that use that step, especially when we start looking at addition reactions later on in this semester. Okay, the bottom line though is when we get to qualifying acidity, you want to go through this checklist to compare two molecules, especially if you don't have the pKa's handy to compare them with. Okay, so or you could use it to help rationalize why there is a difference in pKa. Okay, so for example, if we compare ethanol and propylene, if even though propylene has, probably would have resonance effects when you deprotonate that hydrogen, if you wind up with a negative charge on that carbon, that doesn't matter. The atom is the first thing you want to look at, and ethanol here is going to have a negative charge on an oxygen as opposed to a carbon. So that takes priority, and that's why ethanol has a lower pKa. Okay, so you definitely want to go in order of the different parts of this acronym. So you want to start looking at atoms before jumping ahead to some of these other things, even though you might immediately recognize some of those later ones when you look at a molecule. Okay. Now, that being said, ARIO is a great general guideline, but there are exceptions to it. There are times when it does fail to work properly. You often see this in the case of things containing nitrogen, right? Nitrogen's a pretty electronegative atom, and so you'd expect it to have be pretty good at stabilizing negative charge, yet we often see it acting kind of basically as opposed to rather acidically. Okay, so that's something to keep in mind. So if you looked at, for example, at acetylene here and ammonia here, and you said, well, which of these would be better at getting deprotonated and having a negative 4 mole charge on that atom? Well, you'd say, okay, nitrogen is more electronegative than carbon, so ammonia ought to be a better acid. But if we compare actual pKa values, you will see that the pKa value of ammonia is higher than that of our acetylene here. Okay, so so generally watch out for weird exceptions like that. That's also probably another reason why it's good to know that pKa value for ammonia. Okay, might help to also know the value for ammonium too. All right, so let's have a practice problem here. Go ahead and look at each of these hydrogens and see if you can rank them in order of increasing pKa values. So in other words, you're going from strongest or most acidic protons to least acidic protons. Okay, so go ahead and rank them, again using ARIO to help with that ranking system. Okay, so feel free to pause here. And so hopefully if you've come back now, here are the answers. So let's walk through this and see if we can figure out the rationale behind all of these. So in the first one, we're looking for the A in ARIO. So you want a proton that's attached to an electronegative atom, because that's going to be good at holding on to that negative charge. So out of all of these atoms that are attached to our protons, it's only hydrogen D that's attached to an oxygen. All of the others have our hydrogens attached to carbons. Okay, so hydrogen D would have the lowest pKa out of all of these. All right, so now for the remaining ones, let's see if there's any resonance stabilization from these. Okay, so hydrogen A is in a vinylic position, not allelic, so it's not going to be resonance stabilized by that double bond. Same with hydrogen B, there's no double bonds or anything or lone pairs around to help it, help that carbon get resonance stabilized if it had, a carbanion. Hydrogen C, on the other hand, is in a that carbon it's connected to is in the vinylic position, or sorry, the allelic position to this carbonyl, to this carbon-oxygen double bond. Okay, so there's going to be resonance stabilization for that negative charge on that carbon. Okay, so hydrogen C comes next. Okay, between hydrogen A and hydrogen B is a couple of bonds away from a fluorine, couple of fluorines and an oxygen. So there's some inductive effects that cause hydrogen B to be a little bit more. I think I've gotten that wrong. Nope. Let's stop this here. Between hydrogen A and hydrogen B, it kind of comes down to, is hydrogen B close enough to these electronegative fluorines and oxygen to be kind of influenced from that inductively? If not, and it seems like the answer here is that it isn't, hydrogen A kind of wins the final tiebreaker comes down to orbitals, and hydrogen A is attached to an sp2 hybridized orbital as compared to that carbon for hydrogen B being sp3. So the answer here involves hydrogen A having a lower pKa than hydrogen B. Okay, and that's that final tiebreaker. I would say hydrogen B, it's kind of close here because there's got 1, 2, 3, 4 bonds away. That is kind of a distance, but again, that's, or rather with that negative charge being on that carbon, it would only be 1, 2, 3 bonds away. that's kind of iffy. So that might be a little bit tougher to decide. And hopefully on a quiz or exam you won't have something that is that iffy. Okay. Um, with the second one, whoops, there we go. So here, again, we want to use ARIO. So we start looking at those atoms that our hydrogens are attached to. Again, the clear winner here is hydrogen A, right? We're on oxygen. Oxygen is very electronegative. So that's going to be our most acidic hydrogen, okay? Now, hydrogen B and C are both attached to nitrogen. So we have a tie, we can't use the A in ARIO as a tiebreaker because it's the same atom, okay? You could try looking at resonance and and resonance induction and orbitals, and you may be tempted to immediately jump to orbitals here because you notice that hydrogen C is attached to that sp2 hybridized nitrogen. But remember, you first want to look at resonance. That's the next checkpoint that's the R in ARIO. If you have a negative charge on this nitrogen, if you lose hydrogen B, that negative charge is resonance stabilized with this double bond over here. Okay, notice that this nitrogen is in that allelic position to the double bond we have over here, and therefore resonance causes hydrogen B to be more acidic than hydrogen C. Okay, so watch out for that common trap of jumping ahead to later letters in ARIO just because you immediately recognize something. Sometimes it helps to do this backwards. There are certain cases where you're not starting off with a neutral acid losing a proton to form a negative conjugate base. Instead, your acid has a positive formal charge, and when it loses its proton, you're left with a neutral conjugate base. So in this situation, you can't really look at that conjugate base and determine if that formal charge is stable because your conjugate base doesn't have a formal charge. In this scenario, you probably want to look at your acid itself and see how bad it is at stabilizing that positive charge. So it's kind of, again, like you're thinking of this backwards in a way, but you're still using ARIO. You're still using that checklist in that order of priority to determine which is better or worse, as the case may be, at stabilizing a positive charge. So the better it is at stabilizing that positive charge, the more it wants to stay protonated, and therefore the worse an acid it is. Okay, and vice versa. If it's less stable at holding on to that positive charge, that means it's eager to get rid of that proton, and therefore is a good acid. Okay, so here's a chance to try this out. Here are some examples of some acids that start off with a positive formal charge. Look at each of them and use ARIO to try and figure out which ones are the most stable. Okay, so we're ranking them in order of decreasing strength. So you're starting off with the strongest acid, which is the least stable. Okay, and we're going to work our way towards the worst acid, which is the most stable with its positive charge. Okay, so feel free to pause the video here and take a stab at this. All right, so if you've, hopefully you've come up with some answers. So here are the answers if you want to check them. Okay, you can see that our most stable, our most acidic acid is number D. Okay, and now let's retake this. Okay, so here are the answers, if you want to check to see that you did this all right. If we break this down, we can see that we have three of our compounds with our proton present on an oxygen. Two of them have that proton on a nitrogen. Okay, so using the A in ARIO, you'll remember that an oxygen being more electronegative than nitrogen ought to be worse at maintaining a positive charge, a positive formal charge. So it makes sense that A, B, and D will be more acidic than C and E because A, B, and D will be less stable than the nitrogens in C and E at stabilizing that positive charge. And we see that again in the answers. So we can see that A, B, and D are on the left as the more acidic acids that are less stable, with that positive charge, and E and C are on the right, being more acidic, having, being less acidic, but it being more stable at stabilizing that positive charge and holding on to that proton. Okay, so that's the A scenario. We can then keep working down to try and further parse out this order. So if we look at resonance structures, we'll see that A gets stabilized due to the pi electrons in this double bond being able to kind of alleviate that positive charge on the oxygen. And we see that in D actually gets destabilized. Essentially, the pi electrons moving away kind of, there, you don't see it here, but there's a lone pair. That getting pulled away by these pi electrons causes this positive charge to seem even worse, or make it even like more unstable, and therefore a stronger acid. I think it's sometimes a little hard to see this unless you draw the lone pairs on these molecules. All of these structures here are drawn without lone pairs, and I think that sometimes can help you out. So let's draw these in just so you can see what I'm talking about. So in the case of A, if we look at the electrons around our oxygen, we've got 2, 4, 6 electrons in our 3 bonds. So there must be a lone pair on that oxygen to have 2, 4, 6, 8. It's meeting the octet rule. Okay, so we see here when these electrons swing over to that oxygen, right, we get a more, we have, well, that's an oxygen there. We have 2 lone pairs on that oxygen, and now we have a positive formal charge on this carbon. It's turned into a carbocation. But the bottom line is that positive charge is now delocalized. It's sort of spread out between the carbon and the oxygen. Okay. Now, if we look at D, on the other hand, again, this oxygen must have a lone pair on it. Okay. And so, because that way it would have 2, 4, 6, 8 electrons around it. It needs a lone pair to meet the octet rule. Now, due to the presence of that lone pair, we can't do the same thing as we see in A. We can't have those pi electrons swing towards the oxygen to get rid of that positive charge, because if we were to do that, then this would turn into a double bond, and this oxygen would wind up having 10 electrons around it. It would have 4 from this double bond, 6, 8, 10 electrons around it, and that violates the octet rule. Instead, what we might see for a resonance structure here is actually the opposite. We could have this pi electron swing over here, and have these electrons swing over to this carbon to turn into a carbanion. Okay, so this carbon would have 3 single bonds. There'd be 2 hydrogens that aren't shown here, and it would have these pi electrons turning into a lone pair on it. So it looks kind of like this. Okay, so we have a lone pair over there, and a negative formal, or sorry, a negative formal charge when this happens. But if this were to be the case, what would be the positive formal charge on this oxygen? Well, it would go from being positive 1 to being plus 2. Okay, which is really, really bad for an electronegative oxygen, right? So this is very, very, very unstable. And I think that is why D is the least stable out of all of these, and therefore the best acid. Okay, A is the most stable out of those 3, and that's why it is the worst acid. Okay, it's the best at dealing with that positive formal charge. B, which doesn't have any resonance, is kind of stuck in between over here. All right. So you may be tempted to see this extra resonance structure happening and say, oh, it's got a resonance structure, and therefore it must be more stable, right? This should be a worse acid, but it turns out that the resonance structure for it is kind of dumb. So that's why this one's actually kind of a tricky one, in that D is the best acid out of all of these. That's kind of a little misleading. Okay, let's parse out E and C then. All right. The difference between E and C, obviously, they both have a nitrogen, so we can't distinguish them on the A of REO. There's no resonance there, so we can't use the R of REO. However, notice that we have these fluorines over here. These electronegative fluorines are going to have an inductive effect. But what kind of inductive effect are we looking at? Well, remember, fluorine's electronegative, so it's pulling electron density away from this already positively charged nitrogen. So this difference in electronegativity is going to get starker, which makes this even less stable, all right? And that is why, being a less stable molecule, this really wants to get rid of that hydrogen, and therefore it is a better acid. Okay, it's less stable at stabilizing that positive charge, and so therefore it really wants to get rid of that H plus, and therefore is a better acid. Okay, so that being said, I think I pointed out earlier that we can use this to compare to our acids on both sides of an equilibrium and kind of get a sense of which way the equilibrium is going to go. All right. Now, if you have pKa values, of course, you can do this very quantitatively. You can get a feel for the proportion. Keep in mind that with pKa values, you're dealing with a logarithmic scale. So it's usually 10 to the power of whatever difference we have in pKa's. That tells us the position of the equilibrium. If we don't have pKa's, then we can use REO to determine which of our acids, or conjugate bases as the case might be, is more stable, and therefore which side of the equilibrium is favored. Okay, so let's have a look over here. Here we have an equilibrium between an acid over here. So this molecule on the left is an acid. It's giving up its H plus to this base over here. And you can see here's the conjugate base of that acid, and here's the conjugate acid of the base. All right. So the question now is, which of these sides does the equilibrium favor? Now, you could look at your acid and your conjugate acid and ask yourself which one is a better acid. We don't have pKa values here, so it might be easier to look at our base and our conjugate base and ask ourselves, well, which one is more stable? All right, using REO, we can kind of figure that out. So if we look at our nitrogen, okay, that's housing our negative charge, we can't really use the A in REO here, right? Since the negative charge is it's still in the same type of atom. So that's not really a tiebreaker there. So we next have to look at resonance. We have to see how this negative charge might be spread across resonance structures since we have it in that allelic position to a double bond, whether that double bond is a carbon-sulfur double bond or a carbon-oxygen double bond. Okay, so you can see that if we were to draw resonance structures here, we could have these electrons swing down here and these electrons swing up here, and you wind up having a resonance structure that looks like this. Okay, so the negative formal charge is on that sulfur, and you have that double bond to this nitrogen, which has one lone pair and is neutral. It's got 3 bonds in a lone pair, so that's neutral. That negative charge is therefore delocalized between the sulfur and the nitrogen. Now, the oxygen is going to do the same thing, right? So you still have resonance here, right? Between, here I can draw it out so you can see that a little bit better. Okay, so there's our oxygen. So the difference here, if you see that resonance going that way, so the difference then becomes, well, what is, if this is my conjugate base, which of these is more stable, right? Basically, this sulfur is going to be better at holding on to that negative charge, right? Sulfur is a larger atom and therefore better at, because it's sort of squishier, it's got more electron density to sort of diffuse out that negative charge. This winds up being a more stable conjugate base. So essentially this equilibrium winds up being reactant favored as a result. Okay, so it's kind of, this one was a little tricky in that you've got to kind of look at, you don't have, you can't use the A in REO for the way your conjugate base is drawn, but then when you look at the resonance structures and realize, well, the resonance is kind of tied, while you're looking at the resin structures, you kind of have to use the atoms there. Okay, it's a kind of a combination of resonance and the type of atom being used. Okay, but if you're when in doubt, draw that resonance structure out, um, or just like kind of look at your conjugate base and ask yourself, is this going to be more stable? Is my negative charge going to be more stable on this conjugate base, or sorry, on this base or this conjugate base? Which for either of my bases or either of my anions, which one's stabilizing that negative charge better? Okay, and in this case, this one's more stable, so it makes sense that this side is going to be more stable. Your equilibrium is going to favor this side. All right, so with that in mind, once we know how strong of an acid or base we're dealing with, we can use that information to select appropriate reagents for those acid-base reactions. All right. So if we are trying to carry out a reaction that involves an acid-base step, so let's say we need an acid to protonate a molecule, right? We have to make sure that we have our reaction go in the direction that we want it to. So if we picture this as an equilibrium, right, where our acid is donating a proton to each of these bases, all right, if we're treating each of these as a base and we're going to protonate it, we want to make sure that the conjugate acid that we would make from these molecules would not be more acidic than the acid we used, because then the reverse reaction would be favored, and the reaction we want would not occur. We wouldn't wind up protonating these molecules as we're trying to. Okay, so let's draw this out so you can see what I'm talking about. So here we have, basically an acetylide ion, right? So it's an alkyne, acetylene, or ethyne if you use the IUPAC name, and it's been deprotonated to give it that negative charge. We're trying to reprotonate it. So the original protonated version, okay, so the conjugate acid of this, if you will, is acetylene, and you know that its pKa is 25, right? If we look it up in that table earlier, which or if you try to remember that, that sp hybridized carbon, supporting a negative charge, allows the pKa to drop down to 25. Okay, so we need to pick a base we need to pick an acid that has a pKa lower than 25. All right. If you're having trouble visualizing this, though, you can actually try drawing out an equilibrium to kind of see how this works. So this is your base, and you're reacting it with some generic acid, HA. All right. This gets protonated to go back to acetylene, right? And you have the conjugate base of A, which is A minus, of HA, which is A minus. Now, remember, you want this equilibrium to go forward, right? You want this to take over. So in other words, you need this HA to be a stronger acid than your protonated, ethyne. So this has a pKa of 25. So you need a pKa of less than 25, a stronger acid, for this forward reaction to take over. Okay, so that's kind of the key thing to keep in mind there. Okay, so anything over with a lower pKa than 25 should be fine. All right, so you could use water here. Water has a pKa of 15, right, or in the ballpark of 15. So that works. The reason that anything works here is that this is a really strong base, because this is a really lousy acid. Okay. So in a similar vein, we want to pick acids that have lower pKa's than the protonated versions of the molecules that we're trying to protonate. All right. So if we put a proton here with its negative charges, we would wind up with acetone, a type of ketone. Again, if you look it up in that table earlier, you would see that it has a pKa of about 19.2. So we just need an acid with a lower pKa than that. Again, this is a pretty good base, so it makes sense that you don't need a particularly strong acid to protonate it. Again, something like water would work here. Okay. Now, look at acetate over here. Okay, so if we protonate this, we get acetic acid. Acetic acid has a pKa of 4.7. So we need a stronger acid than that to protonate this, right? So this molecule here, this ion, really, is pretty good at stabilizing that negative charge. Okay, that's why the acid that makes it is 4.7. So if we want to have this go backwards into the acid, that arises from protonating this to make this molecule's conjugate acid, we need something with a lower pKa than 4.7. So would water work here? No, water has a pKa of, in that ballpark of 15. Again, that's way too high for this use. So we need something with a pKa lower than 4.7. So hydrochloric acid would work here, for example. Hydrochloric acid's got a pKa of -7, which is obviously lower than 4.7. So that's an example. Okay. Same thing here. Here we have acetone. If we were to protonate this oxygen, that would be a really strong acid, right? Because it really wants to get rid of that positive formal charge that would be on the oxygen. So the pKa of protonated acetone is -2.9. Right, so again, you want to select something with a lower pKa. So something like hydrochloric acid, sulfuric acid has a lower pKa, so that would work. All right. Now, what if you are trying to do this backwards? Instead of trying to find an acid to protonate these molecules, you want a base to deprotonate these molecules. Well, the same concept applies. If you set up an equilibrium and ask yourself, well, would the pKa of this acid shift my equilibrium to the left or the right? You can figure out an appropriate acid that will push the equilibrium in the direction you want. Okay, so again, let's have a look at some examples here. So here we have hydronium, right? So I'll draw out the equilibrium to give you a better picture of what's going on. So we have some generic base B over here, right? Oh, actually, you know what? I'll draw this as a deep. Oh wait, we are deprotonating. Let me stop this and retake this. So let's have a look at a few examples here. Oh, wait for that to disappear. Okay, so let's have a look at a few examples here. Basically, here we have hydronium, right? And we're looking for a base that would come and deprotonate that and give us the corresponding conjugate acid, which would be water, of course. So let's draw our acid, so to speak, or sorry, our base as the conjugate base of an acid. So for example, if I have, call that A minus, right? That's our conjugate base, we have that coming in and deprotonating that hydronium. Okay, so we have an equilibrium now with HA and water. All right, so we're comparing the relative pKa's of our hydronium over here, which has a pKa of -1.74, and our acid, right, HA. But we want this equilibrium to go forward in this direction. All right, so in other words, we want hydronium to be a better acid than HA. So this pKa needs to be a larger number than -1.74. Right? So we need to figure out something that has a larger pKa than -1.74 and pick its conjugate as the base we would use. All right, so for example, if HA is acetic acid, all right, or even like, let's say it's something like, yeah, actually acetic acid is probably a good example here. Like acetic acid has a pKa of positive, like somewhere in the ballpark of +5. Okay, so we would use acetate, let's say in the form of sodium acetate, as the base that would deprotonate our hydronium here. Okay, which is relatively easy to deprotonate. I mean, -1.74, that's pretty acidic, which makes sense because water is a pretty stable neutral molecule. Okay, but let's have another example here with HCl, right? Here we have hydrochloric acid. which is also a very strong acid. So you don't need a particularly strong base to do this, right? You could use something like hydroxide. I guess hydroxide would be that's a pretty significant. Hydroxide is a pretty strong base because it comes from water, which has a pKa of 15. Okay, but my point here is that as long as you have an acid or the conjugate base of an acid with a pKa greater than -7, that should get the job done. Okay. And so here's a better example of something that has a relatively high pKa. All right, so again, you want a base that is the conjugate of an acid that has a pKa better or greater than 44, right? So again, using my analogy of some thing like A minus here, all right, and I'm deprotonating this, I want HA to be a worse acid than ethylene. Okay. Right. So if this is a pKa of 44, I need this to be a pKa greater than 44. Well, what have we seen that has a pKa greater than 44? Well, if this is an alkane, that would have a pKa of 50, right? So for that, we need the deprotonated version of an alkane, right? So an alkanide ion, right? And basically, so if this is, for example, ethane, we would need CH3 CH2 with a lone pair. We need that resulting carb anion as an example of our base that would be strong enough to deprotonate this. Okay, so yeah. So again, that's kind of how you would process that. You just need a pKa that's greater. You need a conjugate of an acid that has a pKa greater than whatever you're looking for. Okay, so that brings us to the leveling effect. All right, the thing to watch out for here when you have a solvent is that you want to keep in mind the acid-base properties of a solvent that you are using. Okay, this is why, for example, a lot of organic reactions don't happen in water. We don't use water as a solvent, even though we might be dealing with something polar or something that has hydrogen bonding, because water, being amphoteric, can act as an acid or a base, and in some situations it's a strong enough acid or base that it can interfere with the reaction. All right, so you want a solvent to dissolve your reactants and your products, but without actually taking part in the reaction. Okay, so let's see some examples here. So anytime you have an acid that's stronger than hydronium, all right, so hydronium has a pKa of -1.74, you can't use water as your solvent there. Okay, so for example here, we have, an acid of, or well, here's an example of where you can use it, right? So here we have acetate reacting, being present in water, and it's okay for acetate to be present in water because if you look at this equilibrium, acetic acid is a much stronger acid than your water. So if you were to look at the relative extent of this equilibrium, this reverse reaction is kind of taking over, and so your acetate kind of stays acetate for the most part. Okay, this water isn't really interfering with this, and so your acetate stays acetate and it reacts with whatever it needs to react with. Okay, but if you have a if you have an acid that is stronger than hydronium, okay, so if we look at this reaction here, right? So let's say we're using sulfuric acid and we want it to react with some organic compound. All right, we want it to do some reaction. But if we do this in the presence of water, since sulfuric acid is a stronger acid than hydronium, this reaction is going to proceed forward, right? Significantly forward. This is like about 10 to the 7 times a better acid than hydronium. So pretty much all of your sulfuric acid is going to start reacting with any water that's available. And remember, if you're using water as your solvent, there's a lot of water available. Okay, so this would be a situation where water wouldn't be an appropriate solvent. Okay, because it would waste all of your sulfuric acid. Okay? So with that in mind, you kind of want to approach that even with bases. So if you're using a base and you have a base that is stronger than hydroxide, which is the conjugate base of water, you can't use water as your solvent because the water will be a strong enough acid to use up that base and therefore waste it. So you can see here we have an example of an amide ion, which is derived from an amine, okay, so kind of an ammonia derivative. So this is going to be a pretty strong base. Remember, ammonia and amines tend to be an exception to ARIO. They're a much worse acid than you think they are. Okay, so actually, if I recall correctly from earlier in this PowerPoint, ammonia has a pKa of about 38. So even though this is not ammonia, this is an amine, it's going to be somewhere in that 38 to 40 ballpark. All right, so let's say that this is about a pKa of about 38, let's say. All right, and of course this works here for this reaction, right? This is an alkyne with a pKa of about 25, right? So this definitely wants to give its proton to this strong base here. So this reaction is going to go forward, okay? But keep in mind that if you did this in water, okay, and if water were present and it were to act as an acid and give you hydroxide, okay, it would get deprotonated and donate its proton to your amide. Again, you still have the same problem. Water has a pKa of about 15, or like 14.7, somewhere in that ballpark, and it's going to donate that proton to your amide even more readily than your alkyne. Okay, and therefore it'll start wasting this base that you want to deprotonate your alkyne. So that's why water doesn't work as a good solvent. All right, but then neither would something like this alcohol. This alcohol also has a pKa somewhere in that 15-ish ballpark, let's say around 16 or so, and it would also waste your base over here because it is a better acid than your amide. Okay, so you can't use this as a solvent either. All right, so basically you want to pick a solvent that would have a higher pKa than your conjugate acid of your base. All right, so these would probably work instead. Okay, now out of these two, you would think that this alkane with its pKa somewhere around 50 would be a great choice, but this might not be a practical choice. And the reason for this is that in order to do this reaction, you probably need a polar solvent of some sort. You need a polar solvent that can help stabilize these charges. Okay, so the actual answer winds up being THF. This winds up being a good solvent for this reaction because not only is its pKa appropriate, but it's a polar solvent. All right, we call THF a polar aprotic solvent. Now, what do I mean by aprotic? Right? A protic solvent is one that can give off a proton. So water and our alcohols, those are protic solvents because they are capable of hydrogen bonding. Okay, they can donate this hydrogen that's bonded to their oxygen very easily. Okay, so they're kind of acidic is essentially what it gets at. So the shortcut is just pretty much any solvent that does hydrogen bonding is going to be protic. So in this case, it's helpful to have an aprotic solvent because it's going to have a pretty high pKa and therefore not interfere with your base. Okay. All right. So that then brings us finally to the solvation effect. Now, with ARIO, you can use that to help compare molecules and say which one's a better acid, but that's not always the only factor at play. Sometimes solvent also interferes with your pKa values, or with your, um, for seeing something in effect, that, a phenomenon in fact that we can't otherwise explain using REO. So a good example here is with tert-butanol and ethanol. Okay, both of these are alcohols. They have their proton and an oxygen, so that uses up the A in REO. There's no resonance structures here, so that takes care of R. There's no inductive effect, so that takes care of I. And the oxygen's sp3 hybridized, so O is not a tiebreaker. So why does ethanol have a lower pKa than tert-butanol? The answer comes down to how the solvent that that these molecules are dissolved in helps stabilize the negative charge on the conjugate base. All right, so remember, a polar solvent helps stabilize charge by using its own partial charges, right, to surround your negatively charged oxygen on the conjugate base. Okay, so here are the conjugate bases of those two acids. Notice that because your ethoxide from your ethanol is kind of open on this side of the molecule, it can fit more solvent around that oxygen. Your very bulky tert-butoxide, which has this extra carbon, this methyl group sticking out, stops any more solvent getting around that oxygen and helping stabilize it more. Okay, so this solvent effect is what lowers the pKa of your ethanol compared to your tert-butanol. So it's due to this steric hindrance, as we call it, this the bulkiness of this molecule kind of spatially hinders solvent getting towards that oxygen and surrounding it. Okay. By the way, this concept of steric hindrance will be kind of an important one for explaining why a lot of mechanisms turn out the way they do. Okay, it's one of the things I joke about with organic chemistry is that when you want to explain a mechanism, the answer is either sterics or electronics. Okay, so 50% of the time it's this effect of the bulkiness of a molecule stopping something happening that is the reason why something happens the way it does. So something to keep in mind, especially when we start getting into mechanisms later on. Okay, so here's a concrete example of this. So for example, here we have acetic acid, and you probably saw earlier that its pKa is in that ballpark of 5. It's 4.75. That was a pKa in water. If you were to take acetic acid and put it into acetonitrile, which is a polar aprotic solvent, its pKa jumps to 23.5. All right, so what's the reason for this? Well, water is capable of hydrogen bonding, right? And therefore is able to kind of stabilize that acetate ion way better than a polar but non-hydrogen bonding acetonitrile can. Okay, so let's talk a little bit about counterions. Now, counterions are the ions that help balance out a charge. That's the counter in there. So usually you're kind of focusing on something that's doing a particular reaction, but it's charged, and so you need something charged to help balance that out. Okay. But these counter ions don't really do anything. So they're sometimes known as spectator ions. You probably remember that name back in Gen Chem when you learned about double replacement reactions or specifically precipitation reactions. Spectator ions were the ions that belonged to that basically kind of stayed the same in your double replacement reaction. They were the ions of your soluble salt in your double replacement, in your precipitation reaction. Basically, the salt that wasn't your precipitate, right? But the key thing here is that they're present, right? They're necessary, but they aren't, doing anything, right? They're necessary to balance out charge, but they're not actually changing in the reaction. Okay, so we still see these counterions, or these spectator ions, in organic chemistry as well. Okay, that being said, we often leave them out because just like in a double replacement reaction that we want to write out as a net ionic equation, where the net ionic equation is kind of simpler and easier to read because the spectator ions are taken out, we often leave our counter ions, our spectator ions, out of organic reactions. Okay, so look at the example here. We have sodium amide reacting with water to make ammonia and sodium hydroxide. The sodium amide and the sodium hydroxide are both ionic compounds. Okay, so if we were to write an ionic equation for this, they would be split up into sodium ions and amide ions. Likewise, your sodium hydroxide would be sodium ions and hydroxide ions. Well, notice that your sodium ions are not really doing anything. Okay, so that is your spectator ion in this process, in this reaction, and so you can kind of drop it out of your equation to make effectively a net ionic equation. Okay, and that's what we have over here. That's why we leave out. Since the sodium's not really doing anything, it's kind of inorganic and not really carrying out a function, it's not really necessary to write it. At the start of this chapter, I talked to you about the three definitions of an acid and a base, right? I mentioned that we have an Arrhenius definition where an acid gives off H plus and a base gives off OH minus. We have the Bronsted-Lowry definition where an acid donates a proton, donates H plus, and a base accepts it. But I didn't mention that third definition. So if you didn't see it before in Gen Chem, the third definition of acids and bases is the Lewis definition. The Lewis definition of an acid and a base is kind of similar to the Bronsted-Lowry definition. The only difference is it's kind of flipped, where the Bronsted-Lowry definition looks at protons, the Lewis definition looks at electrons. And this is what flips the definition slightly. So in the Bronsted-Lowry definition, an acid is a proton donor. So in the Lewis definition, an acid is an electron acceptor. It's the base that donates the electrons. All right, so you can see that by flipping from protons to electrons, we have to flip the definition, what accepts and donates, the thing we're paying attention to. All right, so that being said, we can pay attention to Lewis acids and bases the same way that we pay attention to Bronsted-Lowry acids and bases by looking at where the electrons are going in our mechanism. All right, so we can kind of basically if we define an acid or a base using the Bronsted-Lowry definition, we can still often do that using the Lewis definition too. Okay, so for example, here we've seen that when hydrochloric acid reacts with water, we make hydronium and chloride. And we've seen that this is your basic Bronsted-Lowry definition, right? Your water is acting as a base. It's taking away this proton from your HCl. And your HCl is acting as an acid. It's donating that proton to the water, right? Well, let's look at it from the electronic standpoint. The lone pair on this water is being donated to that hydrogen. So you could say that water is donating its electrons to the hydrogen, and therefore, by that definition, is a Lewis base. Okay, so in Bronsted-Lowry, water is a base because it's accepting a proton. In Lewis definition, water's a base because it's donating its electrons. All right. Likewise, in HCl, the electrons from this hydrogen-chlorine bond, it's going towards the chloride. All right. So again, HCl is acting as an acid because it's moving its electrons toward. I take that backwards. It's goodness. Let's retake that. Likewise, in HCl, we have our hydrogen that is accepting those electrons from our water, and that's what's making HCl a Lewis acid. All right. So again, it's still meeting the definition of an acid. It's just that we're paying attention to the electrons instead of the proton. Okay. Now that being said, the Lewis definition comes in handy for certain situations where the Bronsted-Lowry definition doesn't work. Okay, so look at this example here. There's no proton transfer going on here, but there is a transfer of electrons. Okay, notice that our water molecule is donating its lone pair into this empty p orbital on our boron. Okay, and it's forming this oxygen boron bond. So, what is our acid and what's our base according to the Lewis definition? Well, water is acting as a Lewis base because it's donating its lone pair to that boron. Boron's acting as a Lewis acid because it's accepting that lone pair. Okay, so again, there's no transfer of protons, so we can't use Bronsted-Lowry here. So using the Lewis definition is kind of useful in this situation. And that's it for this chapter. So I'm going to walk through some additional practice problems here, but and obviously I'll put up the answers. But feel free to ask me any questions on this, and be sure to try out the homework problems that are on Blackboard in the homework document. All right, so here we have some addition practice problems. Just pause the video to take some time to try these out, and I'll go through the answers. Okay, so if you're resuming right now, let's talk about this one. Okay, so here we have an acid-base reaction here. We are starting off with a positive charge over here. So this probably wants to lose a proton. That's probably going to make, I would say this is probably more acidic than this molecule over here. Okay, so let's draw some arrows to show where this oxygen is losing its only hydrogen that's attached to it. Okay. Actually, I think I have that on the next slide. There we go. So we can see that we would be breaking this oxygen-hydrogen bond, and those electrons would go to the oxygen. But in order to start this out, we need this molecule here to act as a base. So it needs to have its lone pair attack that proton. And so we need an arrow going from that lone pair to the proton. Of course, now that means we're going to form a bond between that oxygen and that hydrogen, which of course puts a formal positive charge on that oxygen. And we lose that hydrogen on this molecule, and we wind up getting an extra lone pair, which winds up removing that positive formal charge, turning this neutral. Okay, so that's what those two products look like. All right. So for a base with an especially large value for Kb, will its conjugated acid have a relatively low or high pKa? Explain why using the relative pKa values. You want to keep in mind that with I think what gets confusing with this problem is that we jump from Kb. We use a non logarithmic version of Kb here, just an equilibrium constant. Whereas here, when we talk about the acidity, we're looking at pKa, right? Which, remember, is based on a logarithmic scale with a negative sign, so it kind of flips that expectation. All right, so let's first figure out what we're trying to do here. With a base, we have a large value of Kb. So you should ask yourself, is this a strong or a weak base? So remember, with when it comes to an equilibrium, all right, your Kb is going to be your products over your reactants, right, for any equilibrium constant. And so if by definition a base is one that produces the products more, okay, like that's going to, it's a strong base, it wants to produce products more, that would give you a large value of Kb if you made more products. So a large value of Kb implies strong base. Okay, so what is its conjugate going to be? If it's a strong base, its conjugate is going to be a weak acid. And if it's going to be a weak acid, is it going to have a high or a low pKa? Remember, weak acids have relatively high pKa's because, remember, their Kas are going to be low because they're weak acids. They're not going to produce a lot of products for the Ka of their equilibrium. Okay? So if you want to see Oh yeah, so basically I think the question asked to illustrate this with some relative pKa values, but I think we can kind of just do that, theoretically, and I'm sure you can find some, just plug in numbers, but if you take the negative log of anything and compare it with the negative log of something that is greater, you'll see that you get a smaller answer. Okay, so let's do a comparison of an equilibrium, even though it's written out as a regular reaction arrow. But comparing the pKa's of our two acids here, which side will be favored? All right. So remember, the lower the pKa, the stronger the acid, and the stronger the acid, the more it wants to give off its H plus and go towards its conjugate base. So having an pKa of 5 over here means that this is 1,000 times, right? There's a difference of 3 here, so 10 to the power of 3 is 1,000. HA is 1,000 times a better acid than HB. Okay, so this equilibrium is shifted 1,000 times to the right. In this problem, we want to rank out these bases in order of increasing strength. The question also asks you to rank their conjugates in order of increasing pKa. That should be the same order, right? Because if your bases are getting stronger, that means their conjugate acids are getting weaker, which means that their pKa's should increase, right? So anyway, take a second to look at these using Ario and ask yourself, how can we categorize these, in terms of stability and so on? So feel free to pause this video and think about that. Okay, and if we come back, we can look at each of these examples, and if we're looking at them in terms of increasing strength as bases, another thing to look at is how reactive they are, or how stable are they. For the ones that have negative charges, how good are these at stabilizing that negative charge, right? For the ones that aren't charged, how reactive are they? How stable are, if they're acting as bases and we were to protonate them, how stable are those protonated versions? All right. So let's have a look at how the positive charges on B, D, or sorry, the negative charges on B, D, and E compare. Okay, and if we look at A and C, we can kind of figure out what happens if we protonate them and look at them accordingly. Okay, so out of B, D, and E, B is going to be the strongest base out of all three of those. Okay, D and E both have fluorines attached to them. Okay, so that's whereas B doesn't have any inductive effect, so it doesn't have an electronegative fluorine pulling away on that negative charge and destabilize and sort of stabilizing that negative charge by spreading it out and delocalizing it. So B is relatively unstable, and that makes it a stronger base. Because it's so unstable, it really wants to pluck up a proton. Okay? Now, if you look at D and E, though, they have stabilizing effects that make them worse bases because they are better as they are. Okay? So if you look at D versus E, right, both of them have induction, right? But you've got to also look at the fact that in the case of E, you've got that the orbital that's an sp2 hybridized carbon, and so that orbital winds up making the difference. Even though they both have an inductive effect and they're tied there, it's the O in Ario that helps the tiebreaker. Okay. All right. By the way, if you're wondering why isn't there any resonance effects, why can't this double bonded carbon wind up having taking this lone pair towards it? It won't, because you need to take into account the hydrogens that are on this carbon, and that would moving these electrons over would violate the octet rule. Okay, so if we were ranking these three, basically, if we rank them in order of bases, it would actually go B, D, E from order of strongest to weakest. Okay, so they've kind of listed in reverse here, but remember we want to do increasing. Oh, sorry, I got that backwards. Yeah, B is the strongest. So we do want to go EDB because we're increasing strength of base. Okay, now let's look at A versus C. Okay, which one is going to be a stronger base? Okay, so um, if you pick up, if you protonate A, if you put a proton on your oxygen, it will form a positive formal charge on that oxygen, right? Likewise, if you put a positive formal charge on that nitrogen by protonating this nitrogen, you turn into an ammonium ion, which is relatively unstable. Relatively stable compared to your formerly positive oxygen, right? So in other words, that tells you that C, since it doesn't mind picking up a proton as much, is a stronger base than A is. Okay? So if we were to organize these, C is a stronger base, okay, but they're both worse bases than our negatively charged molecules, which really want to pick up a proton. Okay, so ordering them from weakest base A to stronger base B, it would go A, C, E, D, B.